Thank you very much. I'm here to talk about something very different. I'm here to talk about the power of the stars, fusion energy. So first, let's set some context. I'm a MIT PhD. I love graphs. So this is a graph that's one of my favorites. This is the worldwide energy, clean electricity demand projections. And there's really three things that you need to know about this graph. One, the x-axis is in decades. This is a giant macro trend over the better part of the next century. The y-axis is in gigawatts. Gigawatts are gigadollars. This is on order $100 trillion transition. The different curves are different projections by different organizations whose job is to project these things. And they disagree by a factor of at least 3. And they basically disagree based on how techno-optimist they are. Are we going to meet our climate demands, our climate requirements? And what is the demand impact of things like AI? So here we have a $1 trillion change over decades, and we don't really know how it's going to go, but we know we need new technologies. That's the type of thing that you want to get involved in and go out and try to invent those types of technologies. Well, it turns out that in energy, the universe has already picked a solution. So 99.999% of all the energy in the universe is actually made through this process called fusion. It's the process that's inside of all the stars. It's the process that built every single atom. In the fusion process, the lightest elements get combined together, and they make heavier ones. And in that process, they take a tiny bit of mass and they turn it into energy. E equals mc squared, it's a lot of energy. This is the opposite process to traditional nuclear power, where we take heavy elements and split them. It's a completely different process. If we were to make this process work on Earth, it would mean that you could make energy from basically no fuel. The fuel is elements of water. It's available to everybody. You could make this in a machine that sat there and made energy continuously, a machine that you could build and put it in a power plant, a machine that would make heat, and you would convert the heat to electricity. So at the heart of this is this process that is at the cutting edge of what science can do, built into a machine, something you have to manufacture, put into a plant. And the world is right now at the cusp of being able to do those three things. What these would look like as power plants is you would go and you would make a new class of power device. These would be plants that would be like the order of building a natural gas power plant or building a coal power plant. So these are centralized utilities that you would install potentially where you already had fossil fuel assets. On this picture is our version of that. This is a type of machine. It's called a tokamak. And the world's actually built about 150 of these, but all for scientific research. They haven't yet reached the point where they can actually make power. In our case, this would be about 400 megawatts of electricity. 400 megawatts is enough to power a town. You would need to have on order a few dozen of these to, say, power Dubai. That's similar to how we power Dubai today. These types of power plants are things that could be incredibly sustainable. So when you think about being able to run a power plant with basically no inputs and no emissions, so that's a pretty incredible thing, but that's exactly what the sun does. The sun sits there and it runs for 1 billion years. It doesn't take inputs, and it doesn't really have outputs. And if you built a machine that basically had a star inside of it, that's what you would have for your power source. This would happen without the long-lived nuclear waste. So there's no chain reaction, there's no uranium, there's no plutonium. So that's why many people think that the fusion energy systems are sort of the holy grail of energy. Additionally, when you think about the ability to scale such an energy system, that becomes primarily a manufacturing exercise. It becomes, how do you build these machines fast enough? When you build the machine, you go and you install it, it makes energy, it doesn't consume resources. And you start to look at what the installed footprint would be for building out an industry, a fusion industry, and it's similar to the types of industries we already do today. So factories that make cars, factories that make ships. And so that means this could scale. And it could scale at the rate that would be needed to meet those curves I showed earlier. And that's a really big deal because it gives you a new option for how to both meet the demand growth for energy, where energy is needed around the world for people that don't have it, while also doing it in a clean way, a way that doesn't produce carbon emissions. So we've been developing this at Commonwealth Fusion Systems. What are we? So Commonwealth Fusion Systems is the largest private fusion company. It's just over 1,000 employees and about $2 billion of capital that's been invested on the plan to be able to build the first generation of these fusion power plants in the near term. How near? Like in the early 2030s. It's backed by investors that include Bill Gates and Breakthrough Energy Ventures, and also large energy companies like Eni and Equinor, and sovereign wealth funds like Temasek. It's a spin-out of MIT based on research that has come from the worldwide fusion community over the last 3 decades. And what we're doing is we're taking that science and these types of machines, we're developing new technology to make these machines faster and higher performing to build, and we're building a demonstration machine, the one in the middle we call Spark. And then that would lead on to the power plant I showed earlier on the right called Arc. We're able to do this now, today, because the science about how to make that reaction go is increasingly well understood. About 2 years ago, a lab in California demonstrated that reaction, the fusion reaction, at a performance level that made more power out than in for the first time ever. This was a really big achievement in the history of humanity. And this is a bunch of data on the right. I'm not going to go through the details. But these are all machines that have been built around the world that are going up to the right. They're getting higher and higher performance. So we're getting to the point now where we can predict how these machines work, we can build them, and we can reach the levels of power production and more power out than in that is needed to think about a commercialization effort. So the science is at the cusp. And now the step is to actually build it into industrial scale demonstrated facilities. This is one such facility. This is our facility, Spark. This is about an hour outside of Boston at previously it was an Army base. And this is a prototype of a fusion power plant. In the middle of this facility is where the actual machine is assembled. And then around it are all the different industrial scale facilities that make that power plant run. And we started to build this about 3 years ago. We took an empty site. Here's a picture of the site. Took an empty site and started to build what is the most advanced energy project in the world. So everything you see here is built in the last 3 years, designed by our company. Our company comes from people that used to build planes and rockets and submarines. And we have built a supply chain that has developed all these technologies that can make the fusion machines do what we want them to do. And we're in the middle of putting all this together in Devens, Massachusetts. We're about halfway through this process. This picture here is where we'll actually assemble that machine. That assembly is actually getting started this month. And in about 2 years, we'll turn this on. And so in 2027, what we'll have is a prototype fusion demonstration facility that's about 100 megawatts, so size of a small gas turbine, that will push a button and will make more power out than in from a star in a bottle using a whole stack of advanced technologies, which will be very, very exciting. This is enabled because of these technologies that relate to how you build these effectively magnetic bottles. So this machine itself uses very, very strong magnetic fields that use a type of material that won the Nobel Prize in the 1980s and has been commercialized over the last 20 years. When I said earlier that you could think about fusion as an energy source that you manufacture, here's actually the inside of the factory at Commonwealth Fusion Systems that does that manufacturing. And so in this factory, which is on the same site and built on the same timeline, we have teams that are working around the clock that are putting together the actual fusion components. These are made out of traditional types of materials, metal, welding, things that you could picture doing at scale. It's all in the right configuration, very well thought through about exactly what all the different parts must do, but there's nothing in this facility that you couldn't replicate around the world, that you couldn't build over and over again. And this particular facility makes magnets that are superconducting, meaning they don't use any power, but they're very, very strong magnets. They're magnets that are about 20 times the performance of an MRI machine. And we use those magnets to contain the very, very hot fusion conditions inside our tokamaks. And this is technology that was only about 4 years ago thought to be 20 years away. And so this is part of an accelerating cycle where you're taking technologies that are from adjacent areas and you're rapidly putting them into the fusion application and accelerating it. And so about 2 years ago, we demonstrated the first of these magnets, and that was hand-built. That was built with a small team. And now it's being made at an industrial scale in a factory setting. And in the next 2 years, we'll turn all these into the Spark tokamak and turn it on. And now that leads to what happens after the Spark machine. So the Spark machine is a demonstration machine. It's a machine that's designed to show an integrated capability set, that people working together can actually make these reactions happen on Earth in a replicable way. And that's great. That's the end of the scientific journey for the first generation of power plants, but it's not yet a commercial power plant. And so what we announced last December is we announced the site for the first commercial scale fusion power plant. That's this site here outside of Richmond, Virginia, just south of Washington, D.C. This is a site that's in partnership with Dominion, a major U.S. utility, to actually put a fusion power plant on the grid. This is part of the United States' goal to actually have the first fusion power plant running by 2032, which is a very aggressive goal, but a goal that's now been mirrored by many nations around the world. It's a goal that's similar been announced in the UK and Japan. And we have various initiatives that are happening in China, India, and other places that indicate that we're at the beginning of a new type of space race, a new race for a technology around fusion, a new race for energy. And so this site will be the US, we believe, and our company, will be the first instance in the United States of a grid-connected fusion power plant. It'll sell its power onto the grid, probably to help power things like advanced manufacturing and artificial intelligence models. In terms of timing, this is a site that we'll start the construction on, hopefully around the 2027 timeframe. Right now, we're in the phases of figuring out exactly what the design should be, how we should install it, how we interconnect it, et cetera, what the regulatory structure is. That has to be sorted out for fusion in many places. It's been sorted in the US and the UK. And then that'll put this in line to turn on and operate in the sort of 2031, 2032 timeframe is what we're hoping for. So this is the next phase of our company's evolution, but also of fusion energy. And this really opens up an era where we like to think about energy without constraints. So if you think about what you have in a fusion system, you've got this system that is a completely new way to generate power. It hasn't really happened since we first split the atom in the 1950s, and before that hadn't happened until Edison in the first power plants in the turn of the century. In this case, though, with fusion, it's an energy system that will never run out. It's an energy system that literally the fuel on the planet will last us longer than the planet. And that opens up a new way to really think about energy. And what does it mean to lead in energy? What does it mean to develop energy and deploy it? When energy ceases to be about consuming natural resources and finding and gathering them, and becomes about building technology. And that's a very, very hopeful view of the world. And it's one that today, there's now thousands of people at companies, there's over 50 fusion companies, with governments that are in a race to make that a reality. So I'm excited to be here to share that and watch where this field's going over the next 7 or 8 years. Thank you.